Okay, here's the first update for your performance event, the theoretical lab. This is the speeder in the cop example. Speeder who's driving down the road at a constant speed. This will be the first piece to highlight. Circle given information. It passes a cop parked on the roadside. So common scenario. The cop waits 3 seconds. That kind of sounds like important information, so I'll underline that. Then he pursues the speeder, accelerating at a constant 4.0 meters per second squared. And the question, when does the cop catch the speeder? So I'll also underline this, because that tells me what I'm looking for. So I'm looking for when. When means time. I'm just going to put a T under there. So I'm looking for time. Now let's identify this other information I circled. The speeder who's driving down the road at a constant speed of 20. So this is the speeder. Has a constant speed of 20. Passes a cop parked on the roadside. The cop waits 3 seconds. Then pursues the speeder, accelerating at a constant 4.0 meters per second squared. So there's two giveaways telling me what this value is right here. First, it says accelerating. Second, the units are distance over time squared. So I'm going to put an A under that. That's another piece of given information. Alright, do this problem by generating a data table of position values at 1 second intervals for the speeder and the cop. So let's look at that first. Again, this one's just an example. So here's our data table. There's 3 columns. The first column is the time column. Okay, this is always the if it's in the first column, it's going to be the horizontal axis on the data table. So this is what would go on the x-axis. Okay, that's your independent variable. And then there are 2 people, however, involved in this story. So there's going to be data for both the speeder and the cop. Right, it doesn't matter who you put first. All right, let's analyze the data that was collected, however. So the speeder was moving at constant velocity. So I'm just going to make kind of a note of that to remind myself. A constant velocity of 20 meters per second. So that means after every 1 second, his velocity increases by how much? 20. I'm sorry, his position increases by 20. So he starts, this whole story started at what I guess we could just call the origin, or when data began to be collected at 0 seconds, and every 1 second he's increasing by 20 meters. Okay, he's getting farther and farther from the origin is a way we might describe this. This just increases by 20. Let's look at the cop's data. All right, the story says that the cop stopped for the first 3 seconds. So for this first time interval, 0 to 1, 1 to 2, and 2 to 3, for those time intervals, the cop didn't move. He realized, okay, this guy's speeding, waits 3 seconds, and then he begins to accelerate. Now he accelerates at a constant 4.0 meters per second squared. Okay? So where are these values coming from? Remember, this is position data for both of these guys. Position. Okay, how do I know that? Well, the units are here for me in meters. Okay, so we're going to need a new formula to collect position data. Okay, and so the formula for collecting position data when an object is accelerating, I'm going to sneak it in right here. Okay, is delta x, which means position, is velocity initial, which will say v sub I, delta t plus acceleration times time squared. Okay? Now remember that delta t is usually just the total amount of time, because the initial time is usually 0. So for delta t, you can usually just treat that as the final time. So another way to write that expression would be that the position is equal to velocity initial times time, I'll put that in parentheses, plus the acceleration times time squared. And I'll put time squared in parentheses, okay? So you do need to make sure you square that time value. Okay, so that's how they generate each of those position values. Okay, now let's look at this xt graph over here. Position time graph. Okay, here's the speed. Here's the speeder. Okay, the speeder had a constant velocity. Okay, he's just cruising down the highway, not really paying attention to the speed limit, but he's just moving at a constant speed. Call it whatever it might be. Okay, or I guess we know it's 20 meters per second. Okay, and that's his constant velocity. He's speeding. All right, here's that time interval where the cop is not moving at all. All right, so how do I know that? Well, I could analyze this with tangent lines. If I drew tangent lines on this curve, those two tangent lines have a slope of 0. And as time passes, I know my tangent lines are a little bit off the curve, but those lines are getting steeper and steeper, and we know that on an xt graph, steep lines mean fast. Okay, so there's the cop, and he's accelerating because his xt graph, his curve is getting steeper. Now, I have a question to ask ourselves, so what happens right here? Okay, that would be at about time equals, at about t equals 15 seconds. What's going on? Oh, at t equals 15, let's slide up, look to the left and analyze. Well, they're at the same position. They've traveled the same distance, which would be at about 320 meters maybe at that point. So that's where the cop actually catches up to the speeder. Alright, and so to answer that question, we could answer that question from the data, or from the graph. That would be one way to answer the question. Okay, and possibly in another video I'll give you another explanation of how we could algebraically determine the time that they met one another, or when the cop caught up to the speeder. Alright, also here's your motion diagram. Alright, here's our speeder, constant speed. His velocity vectors are all the same length. Okay, no acceleration arrows above the dots because he's never speeding up or slowing down. Alright, and then here's your cop. Here's that first second where he waited. Here's that second where he waited, and there's that third section, or second, where he waited, and then he began to accelerate. His velocity vectors are uniformly increasing. All right, and another way to prove that is his acceleration arrows are also present. So every time interval, or at each position here, the cop is speeding up. Good luck with the back.